Okay, first we're going to talk about a little bit of blitz review of what we did last class. One of those things was translating a function across the graph. When you translate a function, essentially it means to shift the graph across the coordinate plane. We started off last class with talking about f of x equals x squared. And we talked about how this one in this particular problem is being restricted to the domain of -2 up to +2, meaning that the only values we want on our graph are -2 up to +2 for our x values. Yes, we could plug in other decimals in between. Yes, you could plug in numbers other than those, but when you have this restriction on the domain, it's telling me that my graph is going to go through those points that are restricted to those x values only. And when you plug those in, you do get 4, 1, 0, 1, and 4. And then you have that curved graph we talked about. We talked about taking this and transforming it or translating it 3 units down, meaning from the values of y that you get when you plug in x squared, you are going to move those 3 units down. The x values will not change. The y values will all be 3 less than what they were before. Or in other words, you take the y value here and you subtract 3. What that does is that physically takes our graph and moves it down 3 spaces across the coordinate plane. What that means is we also have a new function g of x represented with the red of x squared minus 3. Because that is what we did. We took this original function we call a parent function and we moved it down 3 spaces. What you will find is that no matter what function you work with throughout the rest of Algebra 2, or any math class for that matter, if you can add a number or subtract a number to the end of the function, you add it to all the y values or you subtract it from all the y values, this will shift or translate the function up or down across the coordinate plane. That is called a vertical translation. We also looked at this with a horizontal translation, meaning we took the same function, f of x equals x squared. We took the same restrictions on our domain. We didn't do the whole entire graph with the arrows on the end. We just took those original points again, and this time we did a horizontal translation, meaning we took this graph and we shifted it to the right, in this case 3 units to the right. If you shift this 3 units to the right, it will move the x values positive 3 spaces. Or in other words, it will move every single one of these, adding 3 to the x value, not changing the y value when you do a horizontal translation. What it would do is it would take this entire graph and it would move it across the graph, across the coordinate plane, 3 spaces to the right. The actual equation is a lot trickier on this one than it is with the vertical translation, where all you had to do was add or subtract a number to all the values, meaning add or subtract to the whole function. We are now looking at adding 3 to all the x's, but that's not what it looks like when you actually write the function. What it really looks like is x minus 3 squared. Here's why. If you take 1 and you plug it in here for x, it's going to be 1 minus 3 squared, which is -2 squared, which is equal to 4. In order to move the graph right 3 spaces, you actually have to subtract 3 from the x values to get them back to these numbers, which gives you a squared value of 4, 1, 0, 1, and 4. What I told you in class is that if you have any function that adds a number or subtracts a number inside the function, meaning like this one in the parentheses here, you will move it the opposite of what you think it should be. Meaning if it's minus 3, that's to the right 3. If it was plus 3, it would be to the left. And so it shifts our graph left or right. Just remember, it's always going to be the opposite. So when you move a graph up or down, it's going to be shifting up or down using plus or minus on the end. When you move it left and right, it's going to be plus or minus on the inside of the function. We do this x minus 3 first, and then we square it. That's the order of operations from way back in Algebra 1. Yes, you can have some graphs that do both. You can have some graphs that move left and right and move up and down. For instance, you might see something that looks like this. X plus 2 squared plus 1. That would mean it would take that U-shaped parabola and move it to the left 2 because you're going opposite, and then up 1. And so left 2 and up 1 would be a point right here for my vertex, and then my graph would open upwards. And we'll talk about why that happens also here in just a little bit. So you have these vertical and horizontal translations. The number on the inside moves it left and right. The number on the outside moves it up and down. Always take the opposite of this number though. So last time in class, we also talked about taking a graph and reflecting it across the x-axis and reflecting it across the y-axis. I am not going to go through in huge detail every single part of a reflection on this one because the functions we used here were functions that were linear, which means it was a line. I'm going to use the textbook to help me out a little bit here. Notice that if I take this guy right here, it goes through -6, my beginning amount, and then it goes up 2 over 1, up 2 over 1. If you take those points and you reflect them across the the x-axis, this one is going to come up here, and this one is going to go down here. So you will see that this graph will reflect across. And I am not sure why that thing switched like that. Probably because, yeah, so it's not going to let me do that. I'll just have to kind of freehand this drawing. It's going to be kind of ugly. Let's try it again. Really bad, really bad. So it reflects across the x-axis. Notice this equation now is down 2 over 1 and begins at +6. That means my new function, when I flipped it across the x-axis, is completely opposite of that one. Or in other words, the new function g of x is equal to the opposite of f of x, a negative times everything. Any function you look at this school year, if you take the opposite of that function, it will flip it across the x-axis. it will always reflect it across the x-axis when you take the opposite of it. Last time in class, we also talked about flipping the graph or reflecting the graph across the y-axis. Meaning, if you have this graph, like we did before, 2x minus 7, you can flip this across the y-axis by reflecting these points that you have here over to here. This point will not move because it is on the y-axis. This point reflects across. This point reflects across from here to here. Even this one up here reflects across the y-axis. What this does is this creates for us another linear equation. Notice again on this one that the arrows are there because I did not restrict the domain like we did in the x squared earlier. And so this graph right here is a new function g of x. Notice that this function, and sorry, I just noticed that they use h of x in your textbook right here. Notice that this function, h of x, is negative 2 over 1, down 2 over 1, minus 6 because the beginning amount is negative 6. Now look at that one compared to this one. Notice that the whole function does not change like it does when we reflect it across the x-axis. When you reflect it across the y-axis, only the slope here changes. Technically, what's happening is anytime you have a function, no matter what kind of function it is, if you plug in the opposite of all the x's, meaning you're plugging in these negative values here, but you take the opposite of them before you do the rest of the function. In this case, it would be 2 times negative x minus 6. It becomes negative 2x minus 6, which actually reflects across the y-axis. And this works for any function that we do this year. If you reflect it across the y-axis, it is taking the opposite of all the x's before you plug them in to the function. All right, so let's do a quick little check of our understanding. Reflect this graph across the x-axis. You may want to pause the video and try it on your own real quick, but then I will put the answer over here. So what we have is we have x squared minus 2. Going back to what we did earlier, x squared minus 2 is a x squared graph, a little parabola, moved down 2 spaces because of the minus 2. So this graph would be here at these points. You could actually figure out the values if you plugged in negative 2, negative 1, 0, 1, and 2. Notice that this one has the arrows because it does not have any restrictions on the domain. We're going to reflect this graph across the x-axis. What that does is that we'll take all these points down here and flip them up here, all the points up top and flip them down here. I reflect it across the x-axis, which ends up looking like this. Now, what is that actual function that we just drew? That actual function that we just drew, if Mr. Harris can actually draw it, right? The function that we just drew is actually negative x squared plus 2 because it is flipped upside down and up 2 spaces. Notice we flipped it across the x-axis by taking the opposite of all of these, and that's what happened. So there's several ways you can look at it. If this is the function given to you, you can take it piece by piece and flip it upside down and then up 2. Or you can go with this one And when you reflect it across the x-axis, it'll still end up being that one because it takes the opposite of all of them. All right, so now what we're going to look at is stretches and compressions of our graph. So notice that this one we have f of x equals the absolute value of x, which is what we did in the first chapter. But I'm going to take it and I'm going to make a table of values because I want you to see what's happening in the values as well. Notice that it does restrict the domain from -4 up to +4, which means on my x's, I could plug in the lowest number, -4, or the highest number, 4, and then some numbers in between. I don't have to plug in -4 and 4, but it does help me maybe get a little bit better picture of the points on the graph. So I'm actually going to plug in -4, -2, 0, 2, and 4. A little bit different than -2, -1, 0, 1, and 2, but the same concept. I'm plugging these in and getting the absolute value. Quickly, the absolute value of -4 is 4. The absolute value of -2 is 2. The absolute value of 0 is 0. The absolute value of 2 is 2. The absolute value of 4 is 4. Because those are the distance from 0. That's what absolute value means. If you were to plot these points, you're going to have a shape that emerges here that is called a V, or an absolute value function graph. Notice that when I graph this, I am looking at only -4 over to +4. Remember that domain is our x values, so I don't have any arrows. This is my original function. G of x, in this case, is going to be 2 times what f of x is from this point right here. If you do that, you can actually get the equation immediately because f of x is the absolute value of x. That is the equation for f of x. You plug it in, 2 times that would be the equation for g of x. It's a little bit easier to get the equation on this one than it was for the ones where we did the reflections and the translations. So then what happens is, if I plug in those same numbers again, I'm going to see something different a little bit here. I'm going to take the absolute value, which would be 4, and then multiply it by 2, which would be 8. Take the absolute value, which would be 2, multiply by 2 would be 4. Take the absolute value of 0, 0 times 2 is 0. Take the absolute value of 2, 2 times 2 is 4, and then 8. And so what you'll see is that up here, I've got a point way up here at 8. I know my graph is not perfect. I've got a point here at -2 and 4, and then +2 and 4. 0, 0 did not go up because I'm not shifting the graph up. I'm actually taking this graph and I'm actually stretching the the y value, by 2. But notice what it does to the graph. It stretches the y value by 2, which means it makes this graph look skinnier. Anytime, any function, I hope you're getting this pattern by now, anytime we deal with any function and we plug in a number in front of the function, we're going to use the letter a times f of x. Anytime this number is a bigger number like 2 or 3 or 4 or 6 or 9 million, it's going to stretch the graph, okay? If that number is a bigger number than 1, it's going to stretch the graph, and it's going to stretch it vertically. Anytime this number right here is between 0 and 1, or in other words, if it's a fraction, like 1/2 times the absolute value of x, it's going to compress it vertically. Basically, the bigger numbers stretch them out, the smaller numbers compress them. What would happen if you had 1/2 times the absolute value of x, like this one, is you would end up with a graph that actually looks fatter or wider, because it would take the whole graph and it would stretch it out. So when you look at this stretching, think of a rubber band. Pulling it, it would make it skinnier looking. When you look at something like this, like a 1/2, think about a stress ball. If you squished it down, it would be fatter. The sides would go out. This is called a vertical stretch or a vertical compression. The same thing essentially can happen if you horizontally stretch or compress by a number that is on the inside of the function. So, for instance, in this case, g of x would be 2 inside the absolute value times x. So we're going to take a look at that one. See if you can pause the video and graph that one and see what happens. All right, so guys, I was trying to do a little bit of fixing here too of this. For some reason, I'm having issues with the technology. So one thing, I made a mistake here. I screwed up on right here. Because our domain in our original function was -4 to 4, when we do 2 times x, we actually can only plug in -2, -1, 0, 1, and 2, because it's going to be double this x before we take the absolute value of it. And so one thing I screwed up on is that these sides of this graph do not actually end up there. What happens is, and I apologize for this, I was trying to get the technology to work with me and erase it. It might jump around a bit when you're watching this video. I apologize. What actually happens here is you end up with this graph actually squeezes in tighter, like we were talking about, like you probably seen happen on the other part of the video that's messed up. But it squeezes in tighter, and it does not keep on going up this way. The domain actually gets smaller on this one here, because the 2 times the x makes it -4 there. So what happens is that we call this a horizontal compression. What it looks like essentially, though, is like the vertical stretch that we did. It looks like it has made the graph skinnier, like the vertical stretch that we looked at back here. So you've got to be careful with the functions that have a number on the inside of the function here. It is actually going to do the opposite of what you think it is in your head. Just like we did when we were moving that graph to the left and to the right, we had to take the opposite of it. We also have to remember, if there's a number right here, it is going to shrink it or compress it horizontally, okay, if it is a bigger number. And if it's a smaller number, like a 1/2, it is going to stretch it horizontally or make this graph look wider across there. So that is a little weird, and we will not work with those a lot, but it happens from time to time that you need to understand that there's a number that could be on the inside of the absolute value. So all of these things that we've done, we've looked at translating a function by sliding it up and down, left and right. We've looked at reflecting a function across the x-axis and the y-axis. We've looked at stretching a function and compressing it. And then you can have some that combine more than one transformation. Notice that this particular question gives me f of x, and it tells me this is what the graph looks like. Then it gives me a new function, and it says, how can you graph a combination of transformations? Notice there's a negative out in front. There's a plus 2 on the inside. So what do these numbers do? If you go back and look at your notes or look at the examples, the negative out in front is going to flip it or reflect it across the y. Excuse me. Sorry, Mr. Harrison, struggling to talk. Reflected across the x-axis. This number here, the plus 2 on the inside, remember to take the opposite of it, and it's going to move it to the left 2 spaces. So if we take this particular graph right here, and we flip it and move it to the left 2 spaces, it is going to give me my new function, my new graph. So what we're going to do, you can do either one first. My personal opinion is to work with the flip or the reflection first, and then go with the left 2 spaces. So if I take this point right here, and 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 this point right here, do I need all of them? No, but it gives me a way to kind of figure out where the new points are going to be. If I reflect this, it's going to be here. If I reflect this, it's going to be here. If I reflect this one, it's going to be here. If I reflect this one, it's going to be here. If I reflect this one, it's going to be here. Notice that my new shape, and I'm just going to kind of sketch this with a little dotted line, has gone and moved and flipped completely upside down. It's reflected across the x-axis. Then I'm going to take it and I'm going to move it to the left too. So I'm going to erase my little dotted line here, and I'm going to move every single one of these points to the left too. So this one's going to go to the left too. This one here, left too. This one here, left too. Now I am going to erase these other ones to get them out of the way. Left 2 on this one. Then I'm going to take this one right here and move it to the left 2 spaces on this one. So that is going to give me my graph shifted left 2 spaces. So now that I've shifted my graph, reflected across the x-axis first and left 2, now I have a graph that goes across from here to here, up to here, down to these points here. Notice it has taken this graph, flipped it upside down across the x-axis, and shifted it left 2 spaces. So you can perform more than one transformation at a time. You could have one that looks like this guy, and it says 1/2 times f of x plus 3. So then what you would do is you would take a half of each one of these points, meaning it would squish it or compress it halfway from here to here. It would compress it to 1. It would compress this down to 2. Compress this right here down to 1.5. Compress this here, this is 5, so compress it down to 2.5. This right here is 7, compress it down to 3.5. So notice it has taken this graph and it has basically made it half as big on all the y values, but it has compressed it vertically, not moved it, so be careful. It has compressed it right here. It has compressed it vertically, okay? So if it's a bigger number, it will not compress it. It will stretch it. and make it taller looking and skinnier in some spots. So then it has a plus 3. Notice where that plus 3 is. That plus 3 is outside the parentheses. So that is where we said this would move it up 3 spaces. So we take this and we go 1, 2, 3. Take this one, 1, 2, 3. Take this one, 1, 2, 3. Be careful with that one. Take this one, 1, 2, 3. And this one, 1, 2, 3. You'll notice that now I have my shape. It's a little bit flatter because it was compressed. And then it has been moved up 3 spaces. So each part of this tells me something about what is happening to my function. So in your textbook, if I am not mistaken, you have these extra examples here where you can actually drag the points and see if you can figure out if you got it right or not. But in your textbook, you also have, let me see if I can find it, a concept summary of everything that we talked about. Horizontal translations are numbers that are added or subtracted on the inside. Vertical translations are numbers that are added or subtracted on the outside. Reflections across the x-axis multiply the whole function by a negative. Reflections across the y-axis plug in a negative for the x, basically opposite of all the x values before you plug them in. Horizontal stretch is when you have a fraction on the inside of the function. Horizontal compressions is when you have a bigger number on the inside. Vertical stretch is when you have a bigger number on the outside, or a smaller number would be a vertical compression. All of those things give me a way to look at any function this year and look at the numbers in these spots and tell exactly what that function is doing, whether it has been flipped or stretched or compressed or moved. This one moves it left and right. Don't forget to take the opposite. This one moves it up and down. You can leave it the same and just moves it up and down. This number right here is a horizontal compression if it's a bigger number, horizontal stretch if it's a smaller number. This negative here, if it's not negative, it doesn't do this. But if it is negative, it flips across the y-axis. This number, if it's a bigger number, stretches it vertically. If it's a smaller number, it compresses it vertically. If there's a negative out in front of the whole function, it reflects it across the x-axis. So all of these numbers give me the ability to look at a function like negative times x minus 4 squared plus 2. First of all, notice that it has an x squared, right? That means it's going to be a shape that originally looks like this. That nice little parabola that we've talked about that goes through those standard points that we've done several times. But what is this going to do? It's going to flip it upside down across the x-axis. What is this going to do? It's going to move it to the right 4 spaces. What is the plus 2 going to do? It's going to move it up 2. Just don't forget the opposite of the things on the inside. So then I could take this graph, I could flip it in my head or on paper. I can move it right 4 in my head or on paper. And then I can move it up 2. And so I know my graph is going to be right 4, up 2, and it's going to be opening down. And so now I have this graph that is here And just by knowing what these numbers do in the problem, I just got my whole entire graph. Now, I did have to remember what x squared looked like in order to be able to do that. So what this does is this gives you the ability to transform one function into another. Sometimes you will also have to look at an equation and just tell what happened. Notice that this one has a negative. It flipped it upside down. It has a 1/3, so it made it wider. So you just look at it and you tell what happened. Okay? Sometimes you will also have to go through and actually write an equation from a graph. In your book, there's an example of this train showing the distance of the train from the station a certain number of minutes after the ride begins. So notice the train goes away from the station and comes back. But look at that graph. Notice it is right 15, up 15, and it is opening downwards on both sides. That would be an absolute value with a negative. It was right 15, so it'll have minus 15. And then it is up 15, so it'll have plus 15. And so what you just found out is you found the equation of this guy right here just by knowing the spots in the function that make it go right 15, up 15, and open downward. That's what these spots do. So all of these work together to become transformations of different functions that we'll look at all year long. So your homework, well, if you finish it before class is over, you don't have to do this as homework, but your homework will be located on page 21 in your textbook, which should be, I believe, page 27 in your interactive student edition. So let me throw up page 21 into this video real quick so you can grab it real quick off of here too. But this will also be on Schoology. But page 21 right here, this is your homework. If you finish it in class, you don't have homework. If you do finish it, you don't have homework. Like I said, if you don't finish it, you'll have to do it at home. Like I said, I believe it is on page 27 in your interactive textbook, if I'm not mistaken. Good luck. Let me know if you need to come see me for some extra help next week. I won't be back at the end of this week.